612, which is on fluctuating stress, fluctuating stress.
That was where everything will end to the next exam.
Yeah, third exam. And what I'm going to do now is not a part of your homework, which is due next. Well, is due on Monday, 15th. This will be a new homework. Okay, so what we're doing now is this. So far, everything we've covered in chapter 6 has been this loads. 0, so there'll be sigma max, sigma min, and sigma max is negative sigma min. Okay, so this is only for loads which are cyclic and they're reversing. So the max and min are 0, and the mean stress is 0. Okay, but most times you don't have a mean stress of 0. You have a non-zero mean stress. So here we're going to talk about loads which are more general loads. So I have a figure from the book which might be a better way of doing this. Insert picture. Okay, so here's a generic loading where sigma mean, which is this thing here, is not 0. If it is 0, then we get what we've done so far. So the equation of something like this curve is sigma equals oh, by the way, this is sigma m, which is the mean, plus sigma a, which is the amplitude, times sine of omega t, right? And omega is the frequency you choose, and time just keeps running, and then so you'll have a pattern which looks sinusoid like this. Now, a few definitions here. Sigma a, sigma a is the absolute value of sigma max minus sigma min divided by 2, which basically implies the amplitude. Sigma m is the mean, as you can see. It's the average of the max and min. And then sigma r, which is here, is the range. It's going to be twice sigma a. It's kind of obvious from the figure. And people sometimes like to define this ratio r, which is the ratio of sigma min to sigma max. And clearly, if r equals, well, r is between -1 and 1, r equals -1. This is called reverse loading. R equals 0. This is repeated loading. And then R equals +1 is steady loading. Okay, sigma, this is the, just put it here. Maximum, minimum. This is the mean. That's the amplitude. And then this is called the range. R is called stress ratio. Okay, that's just definitions. Okay, so as I said, so far we have considered loading where sigma m is 0. Okay, so what happens is when sigma m is not equal to 0, the the procedure for testing is much more complicated because there's one more free variable. Earlier, the only free variable was sigma A, right? You change sigma A, you load it to failure, you get a point, you plot it on the SN curve, you take another sigma A and keep doing that. Now we need to choose sigma A and sigma M and keep doing the experiment. And so this is how we are going to generate a new curve for different values for sigma A and sigma B. So we need to generate SN curve for general loading, right? So what we do is, so we follow this following procedure. So the loading is sigma equals sigma M plus sigma A sine omega t, where sigma M and sigma A are going to be the things which we change. So we choose sigma M, we choose sigma A, apply load or loading for number of cycles. So sigma equals sigma M plus sigma A sine omega t till failure. Okay, so we do that, we see failure, we change the sigma A, sigma M, do the same thing, load it, and keep doing it. So repeat 1, 2, 3 for a range of sigma A's and sigma M's. And create a plot of the strength sigma A sigma M and cycles to failure. So the plot will look something like this. Okay, so what I should show this in the context of what we've done so far. So if you go back a few sections, I think it's here. It's here. Yeah, so this is the SN curve, right? For stress sigma A equals, sorry, sigma mean equals 0. So we got this curve. And now we're looking at a new curve, which looks very similar to this curve, except there are many curves. And these curves correspond to different sigma M's. So this is sigma M equals 0. This is the curve we got earlier. Okay, the one which I showed you just some time back. So we got this curve is from 601 reversed loading, this one. Now, what happens is, as you keep increasing sigma M, which is the maximum stress, you see that this curve starts going down and down. And that's because when the stress increases, right, the net stress on the material increases, it will fail much earlier than it would with a zero stress. So for example, if you draw a line like this, you'll see that when the stress is higher, which is this stress here is higher than that stress, the failure is at a lower stress. So the effect of sigma m is to decrease the life of the part. So because it's more stress. Okay, now for reverse loading, the previous section, we looked at that SN curve, and that's a nice way of plotting it. But for this case, where the load is general, people don't really draw the SN curves this way. They draw a different curve, and that curve is known as uh, it's called the Goodman diagram. And it's a different way of drawing the same data. It's just a plot of sigma A versus sigma M on the x-axis as a function of cycles. So cycles will be, so these are, all these points are lines of constant sigma, right? So what you'll do is you'll draw sigma A instead, sigma M, and you'll do these plots for different n. Just the reverse of what this is. So that plot will look something like this. So the same data, but it's shown differently. Can we find it? I think this one. Okay, so this is another way of plotting SN diagram for different sigma m. So sigma m is on the x-axis, sigma a on the y-axis, and these are the different cycles. So what you notice is that, so this is a low number of cycles, and then this is a high number of cycles. So the larger the number of cycles, the more the part can sustain, last longer, and you can see that happens as the stress decreases. So for a lower stress, that is the sinus amplitude, the larger is the life. Now, what you can do here is you can connect this point to that SUT point. Okay, and when you do that, that line corresponds to what is known as infinite life. So this is 10 raised to 6. This is infinity, or n equals infinity. So as you go to that line, as long as you're on that line, the part will not fail. Okay, so this diagram is called, see, it's called Goodman diagram. Sometimes it's also called the modified Goodman diagram. It's also called the Hague diagram. It's the master fatigue diagram. There's so many names. However, this line, which is called the infinite life line, is known as the Goodman line. Yes, that's the line I want. So this is just showing the asymptote line, SC, SUT. And what we have done here is, let me just mark that up. So this corresponds to n going to infinity. That's the Goodman line I talked about last time. Now, what we can do is we can draw a line connecting the origin O with a slope given by the ratio of sigma A versus sigma M, right? So sigma A is the slope, let's call that alpha, then tan of alpha is slope equals sigma A divided by sigma m. So sigma and sigma m is given to us, and so we can draw the load line. So what we need to understand is that as this load line, as the stress increases along this line, it reaches this point. Uh, okay, that's the point where you will see that it is exactly at infinite life, and you go anywhere beyond that point that is to the right of it, then you'll see that you'll have finite number of cycles to failure. Okay, so we define what is known as a fatigue safety factor, just like we define a safety factor for design. So let NF be fatigue.
Is that N or U?
This one, and fatigue factor of safety. So the fatigue factor of safety is OB, which is the point turning O to B divided by O to A. So this is saying that OB is the maximum stress that can be borne, right? While you really don't want to go to the maximum stress, you want to be somewhere below that. So OA is the stress which is allowable. So that ratio, and we can write that in two ways. One, we can write it as, so so these triangles are similar, OA, sigma M, O, and OB, SM, O. So what we'll do is the side is, so between this triangle and the bigger one, we can write that ratio is proportional to SM, because that's the side of the bigger triangle, divided by sigma M, which is the smaller of the sides. You can also write that equal to, similar to this triangle and the top one. So you can write it as SA divided by sigma A. It's in proportion. The ratios will be the same. Okay, so from this we can write sigma A is SA divided by NF. That is just taking the first and the last equation. We can also write sigma M as SM divided by NF. Okay, so that's basically identifying what's the stress you can impose on the element as a function of this maximum stress SASM, which now lie on that curve. Okay, so that's one thing. The other thing we can do is we can actually model the Goodman line. So we know it's a straight line. It passes through SC and SUT. And so the equation of the Goodman line, so equation for the Goodman line. It turns out it's kind of simple to write the equation if you know the intercept on the X and Y axis. It's simply the X coordinate, which is in this case sigma M, divided by the intercept on the X axis, so that's SM, plus the Y axis, which is sigma A, divided by the intercept on the Y axis, so say equal to 1. So it's the equation of the line for which passes through SM and SA being the X and Y intercepts. That's not right. The Y intercept, my bad, is SE, right? So I should write, so the Y is SE and the X is SUT. And SM and SA is actually a point on the line. It's one specific point on that line. So this is the right way of writing the equation. Okay, but we know that SA and SM lie on the Goodman line. Okay, so what is SA and SM? It's this point, SM, SA. And so we know SA and SM in terms of the load factor or the fatigue factor and sigma A. So we'll just sub that in. So I'll write sigma, what's going on here? So I can sub in sigma m as sm sut plus sigma A is sa se equals 1. Because sa and sm lie on that line. Now what I'm going to do is I'm going to substitute sm and sa using this equation. So let's put 1 in 2. 1 says that sm is sigma m nf, and the other one is sa equals sigma nf. So let me just put that in. So subbing in 1 and 2. We have so we can do a little bit of manipulation on this equation and solve for nf. Solving for nf, we have nf equals sigma a divided by se plus sigma m divided by sut inverse, and this is for sigma m is greater than 0. As you saw, that plot was on the right side of the first quadrant.
Is that to the negative first power?
Yeah. So this is how you'll design the elements just to withstand fatigue loads. You will find what SE is, what SUT is, which we've done. So SUT is a material property. SE is something we've found in we've done in the previous sections as a Ka, Kb, and so on. And then sigma and sigma m are given to you. They are the stresses which will be induced on that element when it is being used. So once you know that, you can find factor of safety. Now you can do this for the other quadrant, which is when sigma m is less than 0. So what I'm going to do is I'm going to show you what this looks when you take data on the other quadrant. So this so far had data only in the positive quadrant, right? This is sigma m is greater than 0. All these circles are data points. And then that line, Goodman line, is basically showing you the line for infinite life. And you can see all those dot circles right to the right half, which means that, or sorry, on top of it, which means that this design criterion is very conservative. That is, if there were points over here, so there are no points over here. And that's why it's conservative in the sense that for this point, you don't really need to be here. You can actually be right here, right? So that's why it's conservative. Anyway, so we can do this same experiment for not only positive sigma m, we can also do it for negative sigma m. And what comes out is a more complicated, well, more points, and you get a plot for both quadrants. So this is what the plot will look like for the first and the second quadrant. Here. Okay, so this encompasses the points, previous points as well as new points. Now, this is also more general than the plot I showed you. That plot, I think, was for a specific material. This is for all materials. And the way this is done is, you notice that there's no SUT like there was in this plot. There was SUT, right? So by normalizing the sigma m with SUT and sigma a with SE, you can basically make a plot for all possible materials you can think of doing these experiments for. Can I blow this up? Okay, so this is for sigma m is greater than 0, this is sigma m is less than 0. This is saying that it is normalized, so it's always 1. That's the Goodman line. Okay, so the interesting thing is that even though this line has a slope on the right side, it's actually flat on the left side, which is saying that sigma m does not affect just write it this. So it's saying that sigma m does not affect fatigue life for compressive loads. In other words, sigma m has no effect. So you could just run this experiment with some sigma m equals 0 or 5, whatever you want, and that will not really affect when there's compression. Okay, so that's only for the negative half, not for positive sigmas. So what we have here is a family, well, 2 lines. One is this line with the Goodman line, and the left line, which is a straight line. And we can write equations for both of them. And that way we sort of cover the entire region from the positive with the first and second quadrant. So let's call this line, this is B and C. So for BC, we saw that the equation is sigma A divided by SC plus sigma M divided by SUT equals 1. For AB, the equation is simply sigma A divided by SE, which by the way is this, right? This coordinate is S sigma A divided by SE. And since that is a constant, that is equal to 1. That's what the equation is. This is for sigma M is greater than 0, sigma M less than 0. Now you can also put introduce a factor of safety. So if you put sigma A NF equal to SE, then you get NF equals SE divided by sigma A. So that's the equation you need for design in the second quadrant. Okay, and remember that in the first quadrant, it's NF equals sigma A divided by SE plus sigma M divided by SUT inverse sigma M greater than 0. So those are 2 sets of equations you need for design depending on the sign of sigma M. Okay, so we've only looked at fatigue design, but when you're designing something fatigue, you also need to be cognizant of static static failures, failure due to plane yielding. So there are these. What we can do is, so we also need to take or design for yielding. Okay, that is for static loading. So if you stress this material under some stress and you keep increasing the stress, will it fail or not? And that we've seen before. It's basically sigma A equals, that's not right. Sigma equals, sigma is greater than or equal to SY. So this is something we covered in chapter, I believe, 2. Right? When the stress when in uniaxial loading, if the stress is greater than the yield strength, then the material will fail. Right? That is because there's basically this point where it goes from elastic to plastic, and instead of waiting all the way till SUT, you just decide that it's whenever it becomes plastic, that's when you will assume that the material is going to irreversibly change its shape and it can no longer come back to its elastic limit and it has failed. So what is sigma here? Sigma in this case for dynamic loads is basically the maximum possible stress, which is sigma A plus absolute value of sigma M. So that in the limiting case will be equal to Sy. Okay, and I'm doing this magnitude because sigma M can be positive or negative. So we've looked at compressive and tensile, right? So we can, so this corresponds to two lines. One line is sigma A plus sigma M equals Sy. And the second line is sigma A minus sigma M equals Sy. So now what we can do is we can plot these lines on a sigma A, sigma M plot, just like we plotted sigma A, the fatigue curves on sigma A, sigma M plot. So sigma A on the y-axis like before, sigma M on the x-axis. So this is true when sigma M is greater than 0, right? When sigma M is greater than 0, sigma M is plus sigma M, and sigma M is less than 0, you'll have to put sigma M as minus sigma M, and that's where you'll have the negative sign. So on the positive spectrum here, you'll have sigma A plus sigma M Sy, and that equation, that line will look something like this, with intercepts of Sy and Sy. So this is positive, and then the equation for sigma A minus sigma M equals Sy will look a reflection of that line. So minus Sy. Okay, so this line is sigma A plus sigma M equals Sy. This line is sigma A minus sigma M equals Sy. Okay, these lines have a name. It's called the Langer lines. Okay, and they predict yielding, right? So if you are on this side of the line, you'll see that sigma A plus sigma M. So it's by the way yielding. So if you're in that limit, which is greater than, you will have yielding. And if you're within this so say triangle, then you will have no yielding. So no yielding in this region. Okay, we're going to soon combine this line with the other line, but we can also come up with a design factor based on these lines. It's simply NF equals the maximum stress, which is Sy divided by the stress which it's subject to. So sigma A plus sigma M with the absolute sign. And so this design factor will be the design factor Ny, where Ny is the design factor based on yielding. So let me write that down. Ny is design factor for yielding. Okay, so we've seen Goodman line and we've seen the Langer line. Now let's combine all of that into a single plot. And that will basically the way we'll go about designing things for fatigue failure. So I'm going to insert the figure from the book. the copy of this. Okay, so looks like a lot of things are going on there. Okay, let's break it down. One at a time. Okay, so what's going on here is, as I said, the infinite life is here, right? This line demarcates going from infinite life to finite life. So anything above this line, the Goodman line, is finite life. Anything below is infinite life. Okay, so that is our Goodman line. So as long as you're in this region, you'll see that it's the Goodman line which determines infinite failure. Now, as you go on the right, you'll see that interesting things which goes on here, which is the yield line crosses into the Goodman line, which is saying that now the yield line determines your infinite life. It's basically going to be the boundary is sort of given by the Goodman line and sort of given somewhere here is given by the Langer line. So this region is, you need to be careful about this region in your design. It happens when sigma m is large and sigma a is relatively small. Like you see that here, the stress sigma m is large and sigma is small, right? So when that happens, you need to be careful because it's the Langer line which determines your failure. Okay, so here also something note here is that yielding occurs before fatigue failure. That is, there's no question about fatigue loading. It will just yield immediately after you load the material. The first cycle it will yield. That's what it's saying. This plot is saying. Okay, so that's one thing. The other thing is these lines. Actually, there's an error in this book, in the book. Well, technically, well. So this is actually, this line corresponds to NF equals 1. Okay. And then if you increase NF, it should be this. So NF increasing. So as NF increases, your stress will decrease. And so that should be the case. This line is NF equals 1. And similarly, this line is NY equals 1. And then as you go down, NY will increase. So if you find NF less than 1, it means that it will be in this region. And if you find NY is less than 1, it will be in the top region. It's like a minor point, but it's not sort of obvious from that. Okay, so last thing before we start solving problems is how do you really use these regions or these equations or these curves? Okay, so the normal thing to figure out is, well, you could have one question is you'll be given sigma m, sigma a, SUT, SC, and told to figure out if this, for that particular loading, it fails in fatigue or it fails in yielding or it doesn't fail at all. So general question might be for sigma A, sigma M, S, UT, of course, SY, and SC, predict which region sorry, predict the failure failure region. So how do you do that? Well, there are two ways to do it. One is, if you're a visual person, you can use the plot. Let's move this down. Okay, so here's how we can do it graphically. So assuming that you know what SY is, SUT is, and SC is, you can draw these lines. You can totally draw this region. So once you do that, so make the below plot using SUT, SC, SY, right? The second step would be plot the sigma A, sigma M that is given to you on the plot. Okay, so let's say we made the plot using the values for stresses, S the strengths. If the sigma A, sigma M is here, you know that it's infinite life. If it's here, is in the finite life region. That is, it's going to be 10 raised to 6, 10 raised to 5, and so on. We've shown earlier. But if it's over here, we know for sure that it's going to yield. The first time you load it, it's going to yield because there's no more fatigue. The question of fatigue here, it's going to yield in static loads. So I'm just going to draw or color the third region, which is not here, which is this region. Okay, so that's all the possible regions in this plot, including this one. And then what we can do is, once we know once we plot it, if it is in this region, it's infinite life. That is, in other words, if for that stress, sigma A, sigma M, this part will never fail. If it is in this region, it's finite life. That is, at some particular cycles, it could be 1,000 or 10 raised to 4 or million, it will fail. The way to determine the number of cycles to failure is we need to do the same things we did earlier. We found equations, we had equations for A and B, and then we have stress equals A times n raised to B. You can use that equation to find the exact number of cycles, but this is going to tell us which region it is. And the third thing is, if it's here, the yellow region, then we know that it's going to yield immediately. So it's called the first cycle yielding. What that means is, that the moment you load the specimen, it's going to break. It's not even going to take that stress. So you clearly don't want to be in the yellow region. If you want infinite life, then you want to be in the blue region. And if you want a finite life, then you will be in the gray region. So that's how you do it graphically. If you want to do it numerically, okay, that is same question. For a given sigma A, sigma M, and all these values, predict the failure region. What you would do is the following. You'll find a factor of safety. So NF equals sigma A divided by SE plus sigma M divided by SUT inverse, or SC divided by sigma A So this is for sigma m positive, this is for sigma m negative, and then you'll find ny, which is equal to sy divided by sigma a plus magnitude sigma m. Move this a little bit. Okay, so once you found this factor of safety, it's as simple as this. If nf is greater than 1, okay, we know that nf is greater than 1, it should be in this region because the factor of safety equal to 1 corresponds to that line. So we know that it is infinite life. If we found that nf is less than 1, we know it's above. But if ny is less than 1, is greater than 1, that means it's in the gray region. So find ny, see if it's greater than 1, it's finite life. And if the third case is if both nf is less than 1 and ny is less than 1, we know it's first cycle yielding. Okay, so there are two ways to do the analysis to figure out which region it lies, if it's going to fail or not fail. So let's try to use this, what we've learned, into a problem, well, several problems, and we'll see how to make this prediction. Okay, a steel bar undergoes cyclic loading with nominal stress. The notch location given as sigma max is 40, sigma min is 20. Stress concentration factor is also given. The ultimate strength is given, the yield strength is given, and endurance limit is given. Okay, we need to find the factor of safety assuming infinite life, factor of safety assuming yielding, and actual region based on given stresses. So this is really the question which I talked about just a while back. That is, how do you identify the region? Okay, so let's first find what we need is, so we know SE, we know SUT, we know SY. We need to know sigma A and sigma M, but we know sigma max and sigma min, so we can find the actual stress using that. So let's find sigma A, and let's maybe put a bar for the nominal value. And I'll tell you why I'm putting a bar in a bit. So sigma A, the formula for sigma A is sigma max minus sigma min divided by 2. And so that is 40 minus 20 divided by 2, which is 10. And then sigma M is sigma max plus sigma min divided by 2, which is 40 plus 20 divided by 2, which is 30. Okay, the reason I put a sigma A bar and sigma M bar is because this is a problem involving stress. So sorry, a notch, right? With the notch, the actual stress is much higher than the nominal stress. So the actual stress is going to be the factor of the stress concentration factor times sigma A. So that's going to be 1.2 times 10, so that's 12, and sigma M is Kf times sigma M nominal, that will be 1.2 times 30, that'll be 36. Okay, so now once we have that, we are set to find the various things which is asked in this problem. So A, find NF. NF, the formula is sigma A divided by SE plus sigma M divided by SUT inverse. That is, sigma A is 12, sigma E is, so SE is 40, sigma M is 36, SUT is 100, inverse equals 1.52. B, we need to find factor of safety, assuming yielding, that's Sy divided by sigma A plus magnitude sigma M. So that's Sy is 85. Sigma A is, and by the way, I use this formula because sigma M is greater than 0, right? This formula is true for sigma M greater than 0, and sigma M is greater than 0. Okay, so 85 plus divided by sigma A, which is 12, plus sigma M, magnitude 36, equals 1.8. Okay, so what we can do is we can use, so the third question asks, C asks us for the find the actual region where this lies based on the given stresses. So we can do this two ways, numerically, which is actually simple in this case. So we know that NF is greater than 1 point, is greater than 1. Okay, if NF is greater than 1, it is infinite life. We can also do this graphically in the following way. We need to plot see, so we need to make a plot of the yield line, and we need to make a plot of uh, the fatigue line, Goodman line. So let's do that. So first one is the yield line. So the what is known as the Langer line. So Sy, Sy, Sy. And I think the value is, see, Sy is 85. And then we need SUT, which is 100, and then SE, which is 40. Okay. So 100 will be approximately here. Okay. And then we need SE, which is 40. So this is 85. So somewhere halfway here. So let's say over here. Okay. So we need to join this line. Let's join it with a different color. Let's make it blue. And then we know that this line goes straight like this. Then use maybe red. Okay. I should put the coordinates here. Okay, so now let's try to put down where sigma A and sigma M is on this plot. This is sigma M, this is sigma A, the y-axis. So in this case, sigma A is 12, sigma M is 36. So 12, sigma A, okay, and sigma M is 36. Maybe it's here. 36, 12, very approximate. Okay, so since it's there, the load line, if you want, you can draw it. You can see that that's clearly in the infinite life region. So what we wrote here is right, infinite life. So that's another way of doing it. Okay, so I have actually 3 questions. This is the first 2 more questions. I think I'll be able to solve 1 more question here, and then third one I'll leave it for you, but I will populate it later on. So the second question is similar. Well, the problem is identical to the first one, except that I've changed the stresses here. That's all it's changed, just to show you how you can get different regions. So what needs to be done is we need to follow the same procedure. And so instead of writing down everything from scratch, I'm just going to copy what I have here and then just modify a few things. Okay, so the solution will change, but the procedure is going to be the same. Let's copy this, and that way I can finish on time. Seem to have messed it up. Hold on. Okay. Okay, let's just start changing the values. So it's 60 and minus 20. So what I need to do is 60 minus 20, and that comes out to be 40. And then we have 60 minus 20. That comes out to be 20 for the nominal stress. So this will change to 40. And this will be 48. And this will be 20 to 1.2 times 20. That will be 24. Okay, so the same, since sigma m is greater than 0, again we can apply the same equations, except these values will change. So we'll have 48 divided by 40, 24 divided by 100 comes out to be 0.69. And then again, SY will remain the same. It's only the sigma and sigma m will change. So it'll be 48 for sigma A, 85 for sigma m, and that factor comes out to be 1.2. Okay, and since we have NF, well, if you see NF, it's less than 1.
1.2.
1.2 is the answer, yeah. Since NF is less than 1, it's 0.69, and NY is greater than 1, we can predict its finite life. Okay, and if you want to do it graphically, we can get rid of this point. We just have to plot the sigma A, sigma m, which is 48, 24. So 48 on the x-axis. Is that right? Sigma m. So sigma A is 48, my bad. Sigma A is 48. So you can see this is 40, so 48 is probably up. And sigma m is 24. So it's 85, so it's somewhere over here, 1/4 of the way. So it's somewhere over here. That's going to be my load line. And you can see that's in the finite life region. Okay, so that's how you would solve this. So there's
That's 24, not 85.
good question. Thanks.